Assalamualaikum everyone. Welcome you all to my lecture. First of all, let's discuss about what we are going to discuss in this lecture. Software testing basically ensure reliability, functionality, and readiness for real-world use. Testing can be categorized by style, which includes exploratory, smoke, black box, white box, and fuzz testing, whereas scope includes unit, integration, and end-to-end test, whereas size contains small, medium, large test, and purpose, regression, acceptance, and self-tests. Challenges like flaky tests, which fail unpredictability, and brittle tests, prone to breaking with minor code changes. Randomness in tests should be controlled with deterministic seeds for reproducibility. Test scope varies from small, efficient tests to large system-wide tests. Exploratory testing, though valuable for early investigation, relies heavily on tester judgment. Unit tests focus on specific functions or classes, while behavior-driven development (BDD) emphasizes user scenarios to align testing with real-world expectations. Let's start our lecture number 19. In this lecture, we will first explore the different type of testing in software engineering, each designed to ensure our software is reliable, functional, and ready for real-world use. In software engineering, we categorize the testing based on different criteria, including style, scope, size, and purpose. Each category plays a crucial role in identifying potential issues early and ensuring our system works as expected. First of all, let's discuss about a style. In style, first we have exploratory testing. In exploratory testing, we manually test a system by navigating through it without a script, like walking through a newly built house without a guide. After that, smoke test. Smoke tests quickly check if the main part of the programs work properly, like giving a car a quick startup to see if the engine runs before taking it for a drive. After that, black box testing. In black box testing, we test the program's feature without looking at the code, just like testing a car's control without checking the engine. After that, glass box testing, which was also known as white box testing, involves looking into the code and testing it from the inside out, like a mechanic inspecting the engine and its part for issues. After that, fuzz testing feeds a random data into the system to find unexpected errors, like pressing random keys on a keyboard to see if anything breaks. After that, boundary value analysis. In boundary value analysis, we test the program's limit by using the value at the edges, like seeing if an app handles the smallest or largest number you enter. But in dynamic analysis, we test how the software runs in real time, observing its behavior, like checking the car engines while it's running. After exploring different testing styles, let's now look into the various scope of testing, in which we have unit test, in which we check individual parts of the software, like testing a single light switch in a house to make sure it works. In integration test, we check how different parts of the software work together, like making sure that kitchen lights and dishwasher can both run without tripping a circuit. In last, we have end-to-end test, in which we simulate a full user journey, like from selecting an item to completing the payment. If we talk about the size of the testing, then we have three types of testing. Small test. Small test run quickly on single functions, like pressing a single key on the keyboard to ensure it types. In medium test, we handle multiple parts interacting on the same device, like opening multiple apps on a phone don't cause it to hang. In large test, we cover different systems working together, like testing if a cloud server can support many users streaming a video at once. After that, we have purpose of testing, in which we have regression test, in which we make sure old bugs don't come back after changes. In acceptance test, in which we final check to see if the product meets user expectations or not. In self-test, we monitor the system's health to keep it running smoothly. It checks itself regularly and warns you if any issue needs attention. Now let's discuss flaky tests, a major challenge in software testing. These tests fail randomly, making it harder to identify real issues. One reason for flaky test is non-deterministic failures, where tests fail randomly, like a light that flickers without any clear cause. They are also vulnerable in multiple processes or multi-node infrastructures, where different parts of the systems don't communicate smoothly, causing unexpected errors. Performance issues or timers can also lead to flaky failures, especially when certain processes slow down due to system load. Randomness in test can cause results unreliable. For example, if a website might load differently depending on the traffic, which might affect the test outcome. That's why it's helpful to always log the seed used in test. This allows us to trace if randomness causing the issue. Concurrency issue can make tests flaky, as unsynced process may cause failures. Also, flaky tests are hard to reproduce due to their unpredictability. Also, some tests are sensitive to the time of the day they run. For instance, they might fail during peak hours when system load is high or other background tasks are active. Brittle test is another significant challenge in software testing as they are highly prone to break with even minor code changes. These tests are often referred to as high maintenance because they need constant updating, especially when any internal details of the software change. Brittle tests usually check private parts of the code. Because of this, they are delicate and quick to fail even if there is even a slight change in the detail they depend on. Brittleness might focus on very specific actions in the code instead of checking the overall result. This makes them unreliable and cause brittle tests to fail with even small and unrelated updates. To reduce brittleness in tests, it's helpful to follow guidelines that focus on testing the expected outcomes rather than the internal workings of the code. Let's discuss the role of the random numbers in software testing. In most settings, random numbers should be deterministic, meaning they generate the same sequence each time they are used. This is important for reproducibility as it reduces flakiness by allowing results to consistently recreate it. The recommended approach for managing randomness in testing involves starting the application with specific global seed and logging it. This global seed allows each part of the system to create a private random number generator by combining the seed with a unique identifier. So each component has controlled randomness. For parallel processes, we can use RNGs to that allow us to fast forward their state. This approach offers a key advantage. It keeps results independent of how many parallel processes are running and avoid changes in results even if the extra components are added or removed. Our next topic is about test scope, which refers to the range of the code each test covers. Test scopes can be either small or large, each offering different advantages and challenges. In small scope testing, each test covers a limited section of code focusing on specific isolated small parts. This type of testing is efficient because the coverage for each test is limited, targeting on essential aspects. Although small scope tests may require an awkward setup, such as using dependency injection or mock objects to replicate parts of the system, they can be created alongside the code under development. With small scope tests, it's easier to diagnose issues since only a limited amount of code is executed, making both the test procedure and results straightforward to understand. This approach is typically faster than broader tests, allowing these tests to run more frequently, giving faster feedback on small incremental code changes. In large scope testing, each test covers an extensive range of code providing a broad system-wide coverage. However, this often leads to redundant coverage where many aspects are tested repeatedly and most results are not checked, which can create a false sense of security. While large scope tests may be easier to set up than mid-scope tests, since these tests depend on the whole system, means issues may not be caught immediately. When a failure does occur, it can be difficult to diagnose, slowing down the debugging process. Large scope tests are also typically slower than smaller scope tests, making them less ideal for frequent test cycles. Choosing the right test scope depends on the specific testing goals, balancing depth and speed to achieve efficient testing. Now let's move on to the exploratory testing, a hands-on approach where developers and testers examine the software to understand how it behaves, often in scenarios that are challenging to set up. This method is commonly used to gut check new code or verify that existing code works as expected, especially in unique situations. It's also valuable in question-answer testing, where testers look for behaviors that developers might not have considered. Now let's discuss about the tools used in exploratory analysis. The main tool for exploratory testing includes the application itself and the REPL environments. REPL stands for Real Evil Print Loop. It's an interactive programming environment that reads a user's input and evaluates or runs it, print the result, and then loops back to await more input and dynamic analysis tools like Call-Grain for tracking performance. However, exploratory testing has some drawbacks. It's often not reproducible, meaning results may vary based on the context to which it's run. To keep track of findings, it's good habit to write down each step and action during testing. Also, it's helpful to think about what to expect to see before the starting. But if we know exactly what should happen, it might be better to set up a unit test instead. Since this type of testing depends on the tester's own skill and judgment, the results can vary and it's harder to even know how much of the software was fully checked. Exploratory testing is really useful for quick checks, early investigations, and one-time tasks. Now let's move on to the unit test. Unit tests basically focus on small, specific parts of the code, usually testing just one function or class at a time. They are designed to check visible behaviors that we know the function or class should follow. It checks the end result, which makes them easier to read and understand. When writing unit tests, it's okay to keep them simple and straightforward. It's better not to add extra logic or create new complexities in the test. Let's look at an example. Here we have two ways of testing a user registration function. In the bad example, the test is complicated. It tries to check each part of the process, first generating password, then attempting to create a new user entry, and finally handling an error if the username is already taken. This makes them test harder to read and understand. In contrast, the better example keeps things simple and focus only on the outcomes. It says that if we register a user with an available username, a new entry should show up in the database with that username and password. If the username is already taken, an error should appear. This is what makes a good unit test. Now let's discuss about the BDD. Behavior Driven Development is a testing approach focused on user scenarios. Instead of testing each piece of code in detail, we look at the big picture of what a user would actually experience. BDD uses a format called arrange, act, assert, which breaks down each test into three parts: given, when, then. This format is easy to understand and helps create tests that are readable and self-explanatory. Also, in BDD, it's a good practice to write tests before we code the feature. Now let's discuss an example of BDD. We are looking at a feature for a TV set that allows the user to turn it on and off. Let's go through this example using behavior-driven development to test a simple TV set. First, we set up the scene by saying, as a TV owner, I want to turn the TV on and off so I can watch it when I want and save energy when I'm not using it. In first scenario, we look at what happens when the user presses the power button while the TV is off. We start with the given statement. Given a TV set that is switched off, where we create a new TV object and confirms it's off with assert. Then in when part, when the power button is pressed, we call the method to press the power button. Lastly, in then part, then the TV should switch on. We check the TV is now on with assert. In the second scenario shows that what happens when the user presses the power button while the TV is already on. We start with given statement, given a TV set that is switched on, and press the power button. In when part, we press the power button again, then again in then part, then the TV should switch off. We check the TV is now off with assert. So the last topic which I am going to present is testables. Testables are the tools which we use in testing to mimic the behavior of real objects in manageable way. When we are writing unit tests that involve complex dependencies, several challenges can come up. Sometimes just setting up the right condition for testing can take a lot of time and effort. To handle these challenges, we have different options. We should use real dependencies which give us the most accurate results but making testing more complex. Another approach is to use fakes and simulators. While they require some setup, they simplify testing. Stubs and mocks can also be useful but should be used carefully. If we rely too much on them, the test might not fully reflect how the system behaves in real situations. Using dependency injections make testing easier by allowing us to pass in code parts as needed, helping create flexible and reliable tests.